Okay, in this video we start our discussion on counters, and we're going to start with what's called an 8 counter. And over here is the diagram of an 8 counter that uses 3 JK flip-flops where the JKs are in toggle mode. It's not shown here, but the JKs inputs would both be connected to 1, putting each one of these 3 flip-flops into toggle mode. Now before we talk about how this counter works, I just want to mention that the term clock in digital circuits, okay, which we abbreviate CLK, that you see as one of the inputs on a JK flip-flop and also one of the inputs on an edge trigger D. Well, the term clock refers to a periodic square wave because lots of times that's what you'll have at the clock input of a flip-flop, is a periodic square wave that's just pulses are happening you know, every certain amount of time. But even though the input is called a clock input, it doesn't mean the square wave has to be periodic. I mean, you can have any sort of square wave at the clock input of a flip-flop. So, you know, you could have a pulse that occurs at this time, and then, you know, say like 5 seconds later you get another pulse, and then like a half second after that you get a third pulse. So even though the clock term means periodic, it doesn't necessarily mean that the signal at the clock input of a flip-flop will be periodic. It can be also something else. Okay, so I just wanted to mention that real quick. Now let's see how this counter works. Now notice that the left flip-flop here, this is where the input, where our square wave's coming in. Okay, right here, this is the timing diagram showing, you know, the waveforms for the input of the counter, which is the clock input of the furthest to the left JK, and then the Q output, okay, which is the output of this first JK that connects to the clock input of the second one, and then QB, which is the output of the second JK that connects to the clock input of the third, and then QC, which is the output of this third JK. So remember, each one of these JKs is in toggle mode, and recall from last video, right at the end, we talked about how when a JK is in toggle mode, the output Q is going to be half the frequency of the frequency at the clock input. So you see QA is going to be half the frequency of the signal at its input. So if you compare QA to the input signal here, you'll see that in the time that we get 8 pulses at our input, QA we get 4 pulses. So see, there was a divide by 2. And then QB is going to be half the frequency of QA. So during the time we get 4 pulses at QA, we get 2 pulses at QB. And then QC is going to be half the frequency of, or excuse me, yeah, QC is going to be half the frequency of QB. So you can see here, for the time we have 2 pulses at QB, we only have 1 pulse at QC. So each one of these JKs in toggle mode is dividing its clock input by 2 in frequency at its Q output. So QA is half the frequency of the original input, QB is 1/4 of the frequency of the original input, and QC is 1/8 of the frequency of the original input. So you may ask yourself, well, why don't they just call this circuit a frequency divider, because that's what each JK is doing. Why do they call it a counter? Well, the reason they call it a counter is because now if you look at the states at the outputs of the JK during the time of each one of these original clock pulses at our input, this circuit is counting in binary. See right here, during the time of pulse 1, QA, QB, and QC are all 0. Okay, so if we make a table here, all zeros. Okay, during the time of pulse 2, well, QA is 1 and QB and QC are 0. So you see we have that. Then during the time of pulse 3, QA is 0, QB is 1, and QC is 0. Okay, during the time of pulse 4, we have a 1 at QA, a 1 at QB, and QC is 0. Okay, then here during the time of pulse 5, we have 0, 0, 1, where QC is 1, and the other 2 outputs are 0. And then here we have 1 for QA, 0, 1. So you see, this circuit of JKs, it's counting in binary, because if we take QA as the least significant bit of binary code and we take QC as the most significant bit, well, here's 0, here's 1, here's 2, here's 3, here's 4, here's 5. Continuing on, during the time of pulse 7, we'd have a 6, 1, 1, 0. During the time of pulse 8, all the outputs are 1, okay, which is a binary 7. And then look, during the time of pulse 9, all the outputs go back to 0. So you see this would cycle back. So 0, 1, 2, 3, 4, 5, 6, 7. 0, 1, 2, 3, 4, 5, 6, 7. Okay, that's why it's called a counter, because you look at the outputs and you have a binary count. Now, the reason why this is called an 8 counter is because there's 8 unique states. 0, 1, 2, 3, 4, 5, 6, 7. Since 0 is a state, that's why there's 8 states and not just 7. See, this 8 counter is counting from 0 to 7 in binary. You count 0 as a state. Okay, so an 8 counter counts to 7, not 8, which is commonly a common mistake. Now, if I want a counter, a higher count counter, I just add more flip-flops. See, if I were to add a 4th flip-flop, that would add another bit in my count, and I'd have a 16 counter that could count from 0 to 15. 5 bits, I'd have a 32 counter, so I'd need 5 flip-flops. Again, each flip-flop has a bit at its output. So, you know, a 5 counter would be, or excuse me, 5 flip-flops would give me a 32 counter that counts 0 to 31. So every time you add a flip-flop, you double your count. Okay, and that makes sense based on what we talked about earlier, because that's just, you know, one of the basic concepts of binary, that each time you add a bit, you double the number of values that you can represent with those bits. Alright, so you should be able to figure out how many flip-flops you need for any type of whole number power of 2 counter, like 4 counter, 8 counter, 16 counter, 32 counter, 64 counter, 128 counter, 256 counter, and so on. In the next video, we'll talk about how you get a counter that counts to something other than a whole number power of 2, like say a 10 counter that counts from 0 to 9, or a 60 counter that counts from 0 to 59, or a 100 counter that counts from 0 to 99.